So the idea of separate and integrate, which you practiced the mechanics of over the weekend, is going to be useful in every lesson that we do the rest of this chapter. So separate and integrate is useful for slope fields. So you can see how you create a slope field and then you separate and integrate to solve for the equation, and the equation matches the slope field that you created. Separate and integrate is also helpful in the concept of proportionality. Which we're going to split into 2 days, because proportionality can go 2 ways. You can have proportionality that is exponential, and you can have proportionality that is something called logistic. So we'll cover exponential today, and we'll cover logistic tomorrow. And then we'll finish up the end of the week with our last application of separate and integrate, which is for other kinds of growth that are not based on proportionality. Okay, so that's kind of the umbrella under which why all of this is grouped under separate and integrate. You couldn't do any of these things individually without the concept of separate and integrate to begin with. So let me talk with you about proportionality. We're going to deal specifically with direct proportionality. There is also inverse proportionality. We're going to deal with that later. We're going to deal with direct proportionality. Direct proportionality is multiplying by a constant. We say you are, twice as smart as you were yesterday, whatever, okay? So, that's directly proportional. The two are related by a multiplier. So it's some kind of multiplier. How we use it in calculus is the following. Something like this. The growth rate of a population is directly proportional to the number of people present. All right, so then your job is to set up a differential equation and solve it. So set up and solve a differential equation, a diff EQ. All right, so let me walk you through kind of how to do that and how separate and integrate fits into that. So we start with the growth rate of a population. Growth rate is always a derivative, and a rate is always with respect to time. And so we've got dp dt. That is the growth rate. Okay, the change of the population over a determined amount of time is called the growth rate, dp dt. It's directly proportional, which means there's a constant. We'll call it k. We don't want to call it c because we already use c for something else. So we'll use k. And it's directly proportional, which means multiplied by a constant, to the number of people present itself. So what variable would represent the actual number of people? P. Okay, so there we just set up our differential equation. Now we want to solve our differential equation. To solve it, we need an initial condition. And so our initial condition is that we're going to assume at time 0, the population is p sub 0. Okay, that's our initial condition. At time 0, the population is p sub 0. It's the beginning. So now we'll use our calculus to solve it. It's reading between the lines to set up your diff-EQ, and then separate and integrate. Justine, you want to try and do the separate part?
Sure.
Okay, what variables should go on what side?
P should go on the left.
Okay.
So it'd be 1 over P dp.
Yeah, or I can just do dp over p, either way. Yep.
Equals K dt.
Okay, great. K is a constant, remember? The variables are p and t. So then we'll integrate both sides. We get the natural log of the absolute value of the population equals, okay, what's the antiderivative of the constant k with respect to time? Kt plus the constant c. Okay, we'll pause here, and this is where we're going to solve for our constant c using our initial condition. So we're going to assume at time 0 that p is equal to p sub 0. So we'll have the ln of the absolute value of p sub 0 equals k times 0 plus c. Now, do we still need the absolute values around the initial population? Population is assumed to be a positive number, or at least 0, okay? And so we can just say the natural log of the initial population is equal to c. So there's our constant. So to finish solving this, we've got the natural log of the population is equal to kt, plus we just found the constant to be the ln of p sub 0. And all we have to do is our last step is to get p alone. And so how do I do that? What do I do on both sides? Use an e, okay? Apply an e on both sides of the equation. So the population alone would be e to the parentheses kt plus the ln of p sub 0, which if we use our algebra, we know is e to the kt times e to the ln of p sub 0, because the addition of powers is the multiplication of its bases. And then we also know that e and natural log can cancel each other out. So I am left with p equals e to the kt times p sub 0, or in a more common form, p equals p sub 0 e to the kt, which is also the same thing as your PERT formula. We just use k instead of r, but otherwise it's the same thing. So PERT comes from calculus. PERT comes from the process of separating and integrating. Okay, it's just when you need PERT in Algebra 2, you don't know any calculus yet. And so your teacher will just say, hey, there's this great formula called PERT, we're going to use it. And you're like, okay. And you just nod and smile and go ahead and use it. Okay, but it actually comes from calculus. Okay, so let's try some that actually has numbers in it. I'll gradually work some numbers into these. The growth rate of a disease is directly proportional to the incidences or cases of the disease itself. Okay, a bioresearch company, okay, a biomedical research lab wants to reduce the cases by 15%. Per year. So we're going to set up a differential equation to model this. and then we're going to solve the differential equation. I really wanted to do an example on the number of lung diseases directly related to vaping, because the numbers right now are staggering, but there's just not quite enough data for me to feel comfortable doing it. The data goes through the end of September. They haven't released October data yet, so, but it's like, it's on an exponential, like, it's crazy, yeah. So maybe by next year I'll have enough data, I can do that one. Okay, so let's do this one. We're going to set up the disease, P, D, X, we'll call it X, it's a bad, X for a bad disease. Okay, dx dt, okay, is equal to K times X. But this time, you actually know the K. Yes. Okay. Correct. A 15% decrease doesn't mean minus 15%. A 15% decrease is represented by the number of cases that remain. We'll always do the number of cases that remain. So it's 0.85 X. And so then we would separate and integrate that. So we would have dx over x equals 0.85 t. The integration is the same, right? So the natural log of the absolute value of x, which we don't need because these are positive numbers of cases, and 0.85 t plus a constant c. The lab would need to know what the initial condition was when they started their research. Okay, I did not include that in it, but assuming that the lab knew what its initial condition was. Okay, and then you would apply e to both sides. So the number of diseases would be e to the 0.085 t plus c. And then you do the same thing with separating times e to the c. E to the c is another constant. So whatever letter you wanted to use to represent that constant, since you've already used c, e to the c would be another constant, or you can just leave it e to the c times e to the 0.85 t. And so there's the model for the number of disease cases decreasing at a rate of 15%. Okay, so we're just going to keep sneaking more. I'm going to give you more numbers this next one. Okay. All right, a chemical compound. That's going to be the next one. A chemical compound is decaying at a constant of proportionality of negative 3/5. Assuming you start with 100 grams, solve the differential equation. So we know it's got a constant of proportionality. We've got a chemical compound. What variable do you want to use this time? I don't want to use C for chemical because why? I don't know. Whatever. J for Justine. Okay. Okay. All right. So So we'll have that. We already know the constant proportionality again is negative 3/5 times y itself. And we've got the assumption, the initial condition, that we're starting with 100 grams. So we will separate dy over y equals negative 3/5 dt. We'll integrate. The natural log of y is going to be negative 3/5 t plus the constant c. And now we know that our initial condition at the outset of time is 100 grams. So that will leave me with the natural log of 100 equals the constant c. So negative 3/5 of t plus the natural log of 100. Exponentiate both sides. Y is e to the negative 3/5 t plus the natural log of 100, which I can simplify to y being equal to 100 e to the negative 3/5 of t. Yeah?
So again, on the last one, why you did like 0.85? How did you know on this one that you weren't supposed to do like
2/5. Very good. All right. When you are given the actual constant of proportionality, then you keep it exactly as it is. Okay? When it's a percentage, that's different. This was a fraction and not a percentage. And so the percentage you need to do with what the growth rate of what you're keeping. All right, last one. Yes, Jerry, you kind of hinted at that. We're going to do a half-life. Okay. The differential equation, and I'm going to give it to you, ds dt equals negative 0.0077 s models the radioactive decay it's an S, sorry. Okay, the radioactive decay of samarium 151. I looked it up. Okay. What? It's like dash, samarium dash 151. Okay. Determine its half-life. So this radioactive isotope, let's determine its half-life. Okay. So ds dt being equal to negative 0.0077 s. There's a shocking lack of information, but you can still find its half-life without knowing any of that. All right, because you have to make an assumption. All right, the first assumption is that when t is 0, s is s sub 0. That's the first assumption we're just going to assume. Okay, I don't know how much there is, so I pick a random amount. Okay, then our question is, when the next t we don't know, but we do know that s will be down to how much? 0.5. Half of what I started with. So I do have the relationship between s sub 0 and half of s sub 0, which is going to be enough for me to find the time it's going to take to get there. All right, we're ready to integrate both sides. Oh, wait, I didn't separate yet. Take it back. Separate ds over s, negative 0.0077 dt. Okay, now we're ready to integrate both sides. So the natural log of s is equal to negative 0.0077 t plus c. we will put in our initial condition that the natural log of s sub 0 is equal to negative 0.0077 also times 0 plus c, so the constant is the natural log of s sub 0. So the natural log of s is negative 0.0077t plus the natural log of s sub 0. I don't need to finish solving the model to be able to solve for the half-life of the time. Now, I want to find my mystery time by changing the s on the left to what? Half. Okay, so I'm going to change, all right, well, if I make this half s sub 0, bless you, negative 0.0077t plus the natural log of s sub 0. All I need to do is solve for t, which means get t alone. So what should I do to both sides? Subtract the natural log. So I have a natural log of the half of the minus the natural log of s sub 0, right? And you know, remember the property of subtracting natural logs? Okay, it's division, right? The division of half of s sub 0 over s sub 0. And what gleefully happens to the s sub 0 terms? Okay, they reduce. So I'm left with the natural log of half is all I'm left with, equals the negative 0.0077t. So time is equal to the natural log of half divided by negative 0.0077. And you can use your calculator to type that in and find it. Does anybody have a calculator handy?
91 years.
Say it again.
About 91 years.
Okay. Approximately 91 years. Yes, you should have 3. What is it, Ricky? Come on, Ricky.
90 point, wait. I got something different the second time I did it.
Uh-oh.
90.019.
90.019. So not 91 years, closer to 90 years. Look at what we ended up with. We were looking for a half-life, and the ultimate final answer was the natural log of half, which connects to the half-life, divided by what number? The constant of proportionality from the beginning. Okay, that's also a formula that shows up in your handbook. They're like, hey, the half-life formula, you just take the natural log of half and divide it by the constant of proportionality. And everybody's like, okay, sounds good. Right? But where does that come from? Okay? No. Mm-mm. Mm-mm. We're doing our hard work in class. Okay? But, Cassidy, you should maybe, I mean, some of the questions are like, show where this comes from. Okay, but unless explicitly asked, you don't need to.